All right. Hello, everybody. I hope you're all okay. So this is our second class of the semester. Let's see, we're going to continue on chapter 1. And first of all, as I said, if you want to ask your questions, the best thing is to first, I will raise your hand and then I will call you. Do you have any questions at this point? If you want to ask something before we start the class. Yes, Tom.
Hi, you don't take attendance in this class, do you?
No, don't take attendance.
Okay, thanks.
You're welcome. Okay, and we record this class automatically, so I hope we don't have the problems last time, but I think we uploaded, Anthony uploaded the lecture. So today we have also Safali, who was not, he was here last time. Safali is the third UTA. Safali, can say hi to the class because we didn't say anything last time.
Hi, I'm Shafali.
Oh, okay, great. Thank you. Thanks for being here. So, so the UTAs, as we said, are going to, monitor the chat. So I'm not looking at the chat at this point. And let's see where we are. First of all, let's talk about the assignment. The assignment 1 is available on Blackboard, so you can find it on Blackboard, and just made it available. But we'll talk about the assignment. It has to do with this lecture, but then you have to upload it on Gradescope, where it's going to be automatically graded. So you should have received Gradescope emails. So if there's any problem, you can let me know, or let the UTAs know about it. But you can raise your hand if you have received an email, or maybe raise your hand if you have a problem with Gradescope. Okay. In any case, just make sure that you that you have the email. All right. So students that have problems with Gradescope, you can just chat with the UTA, with Shafali at this point, and send a message, and Shafali is gonna probably keep track of what the problems are. All right. Okay. So in the previous class, let me share my screen. So in the previous class, we were talking about some introductory C++ concepts, and we were talking about this particular class, the int_cell class, and how it works. It was a simple class. We gave some, talked about pointers, and just going back a little bit. And then today we're going to continue that lecture. So we'll talk about some concepts that probably know, but they're more formalized here. The concept of an L value and R value. So an L value in programming language is an expression that basically identifies a non-temporary object, and an R value is basically one that identifies a temporary object, and usually, or a value that is associated with the object, a literal. And the L values essentially are things that have names. And it's going to be more clear as we see examples, right? And the term L and R is being used because usually the L values are the left side of an expression, and the R values are the right side of an expression, okay? So a function can return either an L value or R value, and the parameters also can be an L value or R value. So let's see what we mean by that. So these are some simple lines of code. And then if you look at it and somebody asks you, okay, which are the R values and which the L values, let's say, is X an L value or an R value? Is X a temporary object or is it going to survive? So basically, X has a name, so it's not a temporary object. It's a variable, and it's going to live on, right? So it falls into the definition of an L value. Same thing. Say the same thing as Y and Z. These are really non-temporary objects. But now, if you see the number 2, that's a literal, so that's called an R value in our definitions, right? And the same thing. What is X plus Y? This expression. Can you call it an L value or an R value?
Is it an R value?
Say again?
Is it an R value?
X plus Y, it's an R value. See, it is not really, you cannot really use it, right? If you think it is as a name, right? It doesn't have a name. It's a temporary object that's generated, X plus Y, and then is assigned to Z. Z obviously is going to survive later on as a name, but X plus Y is an R value because it's temporary, okay? So basically this is the basic definitions here. And we can see that you can see which things are R values and which are L values, right? Foo, which is a string, which is like a literal, basically it is a R value, it's a temporary. Right. So it's obviously L values are used a lot. We have this L value reference, and in C++. So for instance, here we have a string str, which is initialized here into the word fine. But then you can say string $rstr is assigned to str. So this rstr now is, as you see here, you don't say string rstr assignment str, you say string $rstr assigned str. Right? In this case, the rstr is an L value reference, as we call it. Another way to think about it, and that's a good way to think about this, rstr is another name of str. It's just a synonym. So when you say the next line of code is rstr plus equals O, which means that append O at the end of the string rstr, then the string rstr will become what? It was fine, right? It will become fine O. You got O at the end. But does this change str? Will str change as well because you appended a character at the end of rstr? What do you think?
No, because the RSCR was saved in the ref address.
Say again. Can you speak a little bit louder because I couldn't hear you? Yeva is talking?
Because the RSTR was saved, because the STR was saved to the address of the RSTR.
So STR is going to change as well, what you're saying.
No, it's
Yes.
not going to change.
Okay, so essentially, the truth is that STR, I mean, if you run this piece of code, STR is going to change as well. Because when you did this assignment on top, you didn't see, this assignment here is like, you have an L value associated with it here. You have this symbol there that makes it an L value reference. And that means that RSTR and STR are synonyms. So whenever you change something in RSTR, this thing is going to change in STR. Okay, so it's going to change. STR is going to change. Its value is going to be the same as RSTR. The same thing will happen if you change STR, then RSTR is going to change. They're synonyms. They refer to the same thing. And okay, so Yeva, again, question? Yes.
Yeah, hello.
Yes.
You said for assignment 1, we can when we submit on grade scope.
I mean, I'm sorry, you can have a question. I'll go to assignments after at some point. Now I'm doing the lecture.
Oh, okay.
So
No problem.
okay, so usually if you want to ask something related to what I'm talking about, but then we'll talk about the assignments later on. Okay, and you can ask questions later. Stephanie.
Wait, so just to be clear, the only reason that STR changes along with our STR is because of the and symbol?
Yes,
Okay, thank
because
you.
that means that RSTR, yes, it's an L value reference to STR, right? If you didn't have that symbol, then of course, whatever this objects STR and RSTR would have been totally, you know, separate. But because of that, they are synonyms. Same thing. This expression C out STR ampersand STR is it equal to RSTR? It will be true. So when we say true or false, actually this assignment is going to give you true. They have exactly the same thing. Now you see here three expressions under it: string B1 and string B2 and string sub. And basically, we want to see whether this is a legal expression. And the question is this a legal expression? So, Yeva, Geisha. Does anybody want to talk about it? No. Asia, Anastasia.
Yes, it should be legal.
We think it should be legal. However, the problem is that because you have, if you didn't have the symbol that I have before B1, B2, and sub, then that would be legal. But now it's not, because basically the right side of these expressions is an R value, hello, and the left side is an L value reference. So basically this doesn't work, okay? So it wouldn't be legal. All right. However, and this is going to be a strange concept here. You will have you have the ability to do this thing, and you have something called R value reference, which is kind of a weird concept, and we'll see how it's being used in C++. But R value reference is, as you see, we use two symbols here. All right. We don't use one; we use two. Now B1 and B2 and here sub, these variables are now R value reference, so they can refer to temporary objects. So basically what you see here, hello is a literal, so it's an R value. So you can actually do that, okay? And B2 is a literal, str plus A is also literal, so it's an R value, but you can legally do that. It's we will see why you can do that, and why is it useful if you are asking yourselves why do you have to do that later on. But do you have any questions so far? Some people raised the hand. David?
Yeah, when you were talking about an L value reference, on the other side of the equals, wasn't it looking for an assignment for a memory address, but you passed it a variable. So in that line string ampersand RSTR equals RSTR.
Which line? Which line we're talking about?
Third line. Third line.
Yes.
It's looking for
Third line. Yes.
It's looking for a memory address, isn't it? And but you passed it a variable.
You're talking about this one?
Nope, line above.
Talking about RSTR?
That one.
String, right?
Yeah.
Here, okay. Yes, RSTR is a new variable, right? And it has the same, you can think about it as the same memory address as STR. But we don't, an easier way to explain that is that it is an L value, RSTR is an L value. And because we have this ampersand in front of it, and that assignment essentially means that RSTR and STR are, you can say they share the same memory address, or you can say they're synonyms. Whatever happens to RSTR will happen to STR, okay? So yes, this is what happens.
I understand. I just thought you needed the ampersand sign in front of STR as well.
No. So you don't need the ampersand sign of this. That's a different thing. So if you put the STR in front of the ampersand sign is from the STR, then you get the address of STR. But this is not how you do it here, as you see. Okay? You're not going to do it with the...
If the ampersand was in front of STR, you get the address.
Yes, but this is not what we were saying here. This is not what we try to do here. We don't want to talk about pointers and addresses. Okay? So that's a syntactic that's a syntactic thing here on C++, where this is an L value. The ampersand RSTR is the L value. Okay. All right. I think we have a lot of hands, but I want to move along. Who wants to go? Zachary.
Can you go back to what we most recently did, the R value reference, please?
R value reference or L value reference?
R value.
Yeah. All right. Here we are. Just a second. Why it doesn't move? Just give me a second. Yep.
So B1, B2, and sub are still L values right now?
Yes.
Okay, thank you.
Yes. Actually, did I say L value? Sorry, I'm sorry. I have to correct it. It's an R value reference.
So B1 is not an L value right now. Okay.
It's not. Yes.
Okay.
Thank you. Anybody else? Zachary? They have to. Or Keith, maybe Keith.
What is the 2 ampersand sign? So the 2 ampersand
That's
sign.
exactly that's exactly the R value reference. So basically, we will see it more. It's a little bit weird, but we will see it as in the next slide. So the double of them, it means that B1 is actually an R value reference, and basically it is the same thing as hello. So actually B1 becomes hello, if you think about it. But
okay.
It is weird to see it in this type of code. So I would want to continue and see how it's going to be used. Okay, with more examples later on. Okay, so if you have questions about R value reference, just keep them on. All right, Keith and Stefan, do you want to ask about something?
Yeah, I wanted to ask about the last slide. So if you change RSTR, STR changes, does it work like that the other way around? Like if you change STR, then RSTR changes too?
Yes. So because they're exactly the same thing. They're different. They have a different name, but they are the same thing.
Oh, thank you.
They're synonyms. Yes. And last question by Komal. I have to move along.
Hi, can you hear me?
Yes.
So the R value reference, is it referring to the memory address or the string?
At this point is the string.
Okay, thank you.
Yeah. All right. So let's go back to L value references, which are easier to understand. And basically how we use them. We use them all the time, of course, right? So basically, let's see this particular example where we pass a const string, a reference to a constant string in this function, convert first letter. The only thing that this function is doing is taking the first letter of the string and converts it into size underscore t, which is basically a large unsigned integer, all right? So for instance, you can do things like that. Let's see what we see here. We have a variable named a vector of list of strings, which is just a vector of list of strings, exactly what it is. That's this variable name, which basically an L value, right? And then you have a string named bottle. That's like name is a string, constant string is initialized to the word bottle. But now you can see this thing here as this in the line that says which list auto ampersand which list is assigned to a vector of list of strings, convert first letter name. Okay. Now, what does this do? What is which list? So let's say that name is bottle, right? As we have it here. So convert first letter, what will it give us? It will give us an integer, okay, that corresponds to bottle, right? That's the only thing it's going to do. It's going to just take the string bottle, is going to take the first letter. If it's empty, it's going to return 0, and then basically it's going to give you the string. than an assigned integer. And then you get brackets. Let's say the assigned integer, let's say is whatever, 10, doesn't matter what it is. You have a vector of list of strings, bracket 10. So basically that will give you just the 10th list on that vector, okay? And when you say which list dot pushback X, what will happen? Where will you push back this X, in which list? Let's say convert first letter name gives you 2. Stephanie?
Oh, sorry, I didn't lower my hand from earlier.
Okay, sorry. Yeah. All right. So basically, what this tells you now, this is a good use for value reference, is that if you have a complicated expression like vector of list of strings convert first letter name, and you want to use it over and over again, you just make it an L value reference, which means that which list it can be used wherever a vector of list of strings convert first letter name can be used, right? So you can, instead of writing this complicated expression, let's say take this and you say push back X, right? You write it much easier than by using this this technique here, okay? And then maybe later on you want to address this, use this particular which list as well. This particular list, okay? So basically it is good for simplifying large expressions like that, because you can use the synonyms, right? Now, a question, let's say that you didn't, just annotate something here. You didn't have this thing here. Let's say you have auto, and basically auto essentially is the same thing as a list of strings, right? If you didn't have this ampersand over there, what do you think would have happened? I mean, this piece of code would work. Yes, it would work. Yes,
I think it will
that's
work, but
that's
it'll be more of a.
It'll be a copy.
So again, it will be a copy. So this vector of list of strings convert first letter name is a list of strings, and it will be copied to which list. And then when you push it back, you will copy this X to which list. And maybe this is what you want to do, but it's going to be totally different than what we are showing here. So if you don't, what we're doing here basically is you're actually changing a vector of list of strings convert first letter name. You're changing this, let's say convert first letter name is 2. You're actually changing this particular list, okay? So if this is 2 here, I don't know what I'm doing, sorry. Anyway, if let's say this function convert first letter name returns 2, so what you're doing, you are changing, you are pushing back to the second item in that vector, the third item in that vector, actually, 0 and 2. Okay, so that's how we use it here. All right, sorry. I'm trying to, something is happening on my computer, it's not responding. Let's see. All right, finally. Okay, A second vector, a second use of this L value reference is basically we use it, and we saw this example, for instance, in range loops for in a range loop. So, for instance, here for auto absent x a vector. So basically, x goes through all the items of the vector 10, 3, 4, whatever. But actually, it's a synonym to that particular location, which means that when I say plus plus x, x is going to change to, let's say it starts at 10 because the first item of the vector is 10, then x will become 11, but that means that also the first location of the vector is going to become 11. Essentially, by doing that, you're changing the items of the vector. You add 1 to each item of that particular vector. Okay. And basically, we saw that before. The very important is to avoid a copy. Sometimes you don't want to do a copy, and you may have, but you're doing it because you're not careful about how you use the cell value reference or not. So here, let's say we have a function called find max1, which basically just finds the maximum of that constant vector that we have here. So let's see the functions in the next slide. So basically, I mean, it's the same thing as find max2. So for instance, that's basically the function, okay? It just gets a vector of strings, a constant vector of strings, a reference to a constant vector of strings, and it just looks through the indices and then finds the one that has the maximum value and then returns that string, okay? Simple function. Now, the only problem with this new function, it may not be a problem necessarily, but this result is going to be a copy, right? So but let's say the maximum string from a vector, I guess, is what, zebra, okay? If we have lexicographic ordering, which means that result in option 1 would become the string, a new string that contains zebra, okay? It's a copy. Now, you can do it in a different way, and you can use this function here, which is exactly the same as the previous one, okay? Find max2 is the same as find max1 in all aspects. So the code is exactly the same. The only thing that is different is the return value. So it's not the same function. The body of the function is the same, but the return value is different. It's a constant string reference. So basically, it's an L value reference, a constant L value reference, find max2, right? So what we'll see here now is that when you do that constrict % result equals find max2, what do you think happens? The result will, the find max 1 and 2 will work in the same way, which means that the result is gonna, the maximum string in that vector is zebra. So result will be zebra. But now, because it's, as you see here, is an L value reference, actually, result is not going to be a copy of zebra. Result is going to, in some sense, point inside the array, okay? Result is going to be zebra the way it is in the array. It's not going to be a new memory allocated to it, okay? It will be a synonym to the second element of the array, zebra, okay? Does it make any sense? Yiva, yes.
Yeah,
Yes?
so option 2, we will turn a left value reference to zebra.
Yes. Yes.
Okay.
So basically, yes, basically, if this is the array, it has 3 elements, okay? Then this basically is going to be essentially going here. In some sense, is going to be a synonym to the second element of the array, but it's a constant L value reference, which means you're not allowed to change it, okay? So now result cannot change. You don't change result, which means you don't change the second element of the array, all right? But this is that because find max2 returns a constant L value reference as we see it. Sky.
So basically it does the exact same thing. It just doesn't take up any more space.
Doesn't do a copy. You may want to do a copy, but sometimes you don't, okay? So in this case, you don't want a copy.
Okay.
But you have to know what you're doing. Yes. Charles.
Hey, Professor, would you normally recommend that we always use const when using when returning a reference to avoid changing the original?
Yes, that's the default behavior, but you could return, if you want to change the original, you have the, you are the programmer and you have the freedom to do that.
Thank you.
Yes.
Professor, so like, I just want to go back to auto. So in this case, can you do auto ampersand result and still get the same non-copy?
Yes.
Okay, so all you need to do is auto ampersand result. That will get the const in the string.
Yes.
Okay.
Because findmax2 returns a const string reference, so you will get it from there. All right. Okay. Now. Zubair, is there a question? Because my computer is stuck. Yes. Do you have a question here? No. All right. I will stop actually annotating because now my computer is frozen, so I have to wait a little bit until like that. All right, live and learn. So we will not annotate. I will use second machine next time, but now I have to get out of it. Finally, okay. All right, so I can do that. All right, we'll continue. We talked about these ideas. And of course, we know about parameter passing in C++. And you have you can pass by reference, you can pass by constant reference, or you can pass by value, right? So let's see this example. So here, whenever you pass a big vector, a vector or a list or something that may hold a lot of memory, and if you don't want to modify it, you don't really pass it by value. So this vector of integers ARR has to be passed by constant reference. Otherwise, you will have a copy of a big object that is totally unnecessary. Okay, so as a rule of thumb, in most cases, you pass if the parameter is not changing, then you pass it by constant reference, not by value. The offset here is a double, so you can pass it by regularly. It's a small thing, and you pass it, and there's a copy, so it's fine. The error flag, additional flag, is you pass it by reference because it's going to be changed, it's going to be reflected. You want to see these change. So as we said, call by value, basically small objects that will not be changed by the function. Call by reference, object that may change by the function, be changed, and call by constant reference, everything else. And usually a lot of things going in call by constant reference, vectors, lists, etc., that you don't want to modify. You will pass them as a constant reference. Now we can go back to this R value reference, and you see these two functions here. Let's see, they have the same name, but they're not the same because they have a different type of parameters. So the first one, random item, the first one takes a constant reference, ARR, and the second one takes an R value reference, okay, ARR. Now, the values of the function are the same. The only thing that happens is just gets a random element in that array and returns a random string. Okay, so what is the difference of this function? Let's say that we have this vector, hello, comma, world, and you call random item v. Which version of the two will be called? So you pass it with v is an L value, basically.
Version 1.
It'll go to 1 because these two functions are different in the sense that the first one expects a L value, the second one expects an L value reference, and the second expects an R value reference, okay? But if you call this function here, a random item, and then you pass a literal, essentially, hello, comma, world, which is a vector that contains hello and world, then which version is going to be called?
Version
Would
2.
the second one be called?
The second version will be called,
Yeah,
right?
because the first one is constant. You couldn't really change
No,
that.
no, no. It's not about the constant fact. Yes, it doesn't have to be a constant vector. It can be any vector, and you can the difference between these two functions, like I can just call it this way. It will still work, right? It's gonna go to random item v. It's gonna use the first version, okay? Because it is an R value, an L value, I'm sorry, an L value. V is an L value here, right? But this parameter here, hello world, is an R value, right? So it cannot, so the compiler is going to go to this particular version, the second one. And I think you can, you know, I have this piece of code, the test function that I think I provided to you, right? So it has all these examples, you can try them, right? And you can actually see them for yourself. So for instance, there is this example here, test function for random item. So there are these two versions of random item with the L value reference and a random item with, you see, has the double %, which is an R value reference. And then when you test these random items, when you pass an L value to random item, then it will go to this first version. But when you pass a R value, it will go to the second version, version 2, right? So if you run it, let me make it. I mean, it has other functions where to test, but you will see that it will go first to first version, and then it will go to second version as you expected, okay? Let's see if there's another example here. All right. No, I think we're good. Okay, so you can test that. You can use this piece of code to verify what we're talking about here. So to just see it for yourself in action. Komal.
I'm sorry, why is V a L value reference?
Well, V here is an L value. I'm sorry. Right? It is a name of a string. So basically of a vector. So basically it's not a temporary value, right? It is initialized to hello world, but it is a named variable. So it's definitely an L value. Now, when you look at this first function, a random item, it takes as a parameter an L value reference, right?
Right.
ARR is an L value reference. So it expects an L value.
Oh, okay, I understand. Thank you.
Okay, so it's an L value. It is a reference to N value. So basically what this means is that this ARR, and this, you know how you do this all the time, so ARR, basically when you have a random item V, ARR basically, you can think of it as a synonym of V. There's no copy, nothing is changing, right? It's an L value reference. And basically you just get the random item. But here in the second version, you have hello world. So here you pass an R value, hello world on the second, in the third line here is an R value. So it will go to this second function because second function accepts an R value reference. So basically expects some kind of an R value associated with it. And you see why this is important. You may see why are we doing that here. We'll ask yourself, but you'll see why it's important as we move along. Right now, if you didn't have the second version, if you didn't have this, if you had only one version of these functions, okay, if you had only the first one basically and not the second one, then things will still work. Mean the random item with the literal will go to the first version. Okay, basically the compiler will make the change from this R value hello world to a temporary L value, and it's gonna give it to random item. Okay, but if you have both of them, then it will go to the second one. All right. And again, we saw that before. You can return by value, or you can return by constant L value reference, or you can return by L value reference, right? Or return by reference. So return by value, you just return the object here. That's a templated function. We just return the actual object. And you can return by constant reference. We saw that before when we don't actually do a copy. Let me just finish my, and basically, here we have large type item one, random item one vec. Essentially here we have a copy, right? Random item one returns the actual, the return is object. The return is not a reference of any type. So here we have a copy. But as we saw before, we saw that in the previous example, the second version returns actually not a copy. It returns a reference to the actual array. All right. There was a question that is it still relevant? All right. So let's talk about this function now, this function partial sum, okay? So the only thing that this function is doing, it just it creates a new vector called result in it, that's the same size as the vector ARR, R, whatever. And then basically does some processing. So result 0 is array 0, result 1 is array 0, result 0 plus array 1, etc. So it does partial sums, but result is a different vector than ARR is changing, and just being returned, right? Now, can you return this by constant reference? Can you say vector int constant reference partial sum? What do you think? The problem here is that you cannot really use constant reference on reference in your return value here. Why? Because result, the thing that you return, is actually a local variable in the function, so it wouldn't exist after it, okay? In all the other examples that we use these constant reference things, all right? Here, for instance, where we set the second option, we return a constant reference to the object. We have an array, which is a vector of objects, and we return something within this vector of objects. So basically, it's something that's being passed to the function, and we just refer back to it. But here, result is a local variable, so you cannot really do it, okay? However, you just return it. But essentially, the good thing is, again, it's very efficient. So essentially, what will happen is that a copy is not going to happen, but essentially C++ is going to move, and we'll talk about this, move the result to sums. Okay, so the local variable result is going to be moved to sums without really be doing a copy. So this is efficient, so you don't have to worry about that. So, and now that we went into moves, let's talk about the swap and move operator. Okay, so the STL containers like vectors, lists, etc., contain an operation called move. Excuse me. And that may be kind of weird, but essentially the only thing that move is doing is that it's casting the right-hand side and makes it a R value reference. All right. So let's just see the last line of this slide. And you say here, vector string temp is assigned to move of X. Okay. Now, what's happening here? If we didn't have the move, if you go to the last line and remove the std move, and you say vector string temp is assigned to X, a copy of X, temp will be a copy of X, right? When you do it in this way, X is going to be moved into temp, and then X basically may be irrelevant after that. Okay. And let's say what we mean by that. let's use this piece of code. So here we have a swap. We're swapping these two strings. We have a vector of strings x and a vector of string y. We pass it by reference because we're doing a swap. But let's see how this swap is extremely inefficient. All right, see what's happening here. We have, let's say x has 1,000 elements and y may have another, 2,000 elements. Doesn't really matter. They may be big. So the first line, temp assigned to x, you create a new vector, you allocated memory, and you copied all the elements of x into temp. The second line is basically you get all y into x, okay? A very big operation, okay? Copy item by item. And the third line is you copy all the items from temp into y. So you have done a lot of copies, and then temp is going to be deallocated when the function is, when it's out of scope. So you allocate memory for temp. Let's say x and y have 1 million items. So you allocate memory for 1 million items. You do 1 million copies from temp to x, from x to temp. You get another million copies from y to x, then another million copies from y to temp. And the only thing you want to do is just swap the items of these vectors. All right. Why don't you change the names of the vectors or something like that? So this is totally inefficient, but obviously there is a better way of doing that. And the better way of doing that is this first function here that you see. A void swap is the same signature, but now you say temp is assigned to the move of x, okay? And x is assigned to the move of y, and y is assigned to the move of temp, okay? Now, this move is very crucial here, and it does it very efficient. Of course, you don't really need to write this function. We show you how it would be implemented. You can just, there's a function called swap in the STL. You can swap the items of strings, of vectors, of vectors of any type. But that's how you should implement it, using this move semantics, all right? Let's go back to this move and see what it means, essentially. And we can see how you can make your own move operator. So the first line, temp, is assigned to std move x. Essentially, the only thing that is happening here is that, the way to think about it is that temp becomes a synonym to x when x is an R, but x is now an R value reference, which means it's temporary and may be discarded. So we can think about it in this way. Now, x, the second line, becomes a synonym to y in some sense, right? X gets all the items of y, and after if you go back here, when you see std move of x, then x exists as a variable, but after that it may be empty, it may be something different there. So temp, the operation here takes charge of this aspect, the fact that x can be temporary at this point. It doesn't deallocate its memory, but it could if it wants to, and then gets the values, all right, of x, of temp. Same thing here. The second line, x, y, and the third line is y is assigned to x. And that's basically what is done. It's extremely fast. There's no really copy, okay? I don't know how clear what that was. Do you have any questions? Yes, Adam. I cannot hear you. Can you speak louder? Hello?
Yeah, hold on. Can you hear me now?
Yes, yes.
Does the X and the Y have to be the same size?
No, they don't have to have the same size. All right. So all these things that you see, Resham, Nahim, yes, go ahead.
So basically, after you move x and y, so x would be empty, or temp would take over x.
Well, at the end of this operation, x and y will be swapped. They will not be empty.
Oh, okay.
At the end, But
Okay.
here, for instance, when you do that, X, so it depends on how vector implements this operation here, the move constructor, as we call it. So temp is constructing, this is called the move constructor, the first line. The second line is called a move assignment operator, and the third line is a move assignment operator. Okay, so
Okay.
that's why
Okay.
we call them the big five, right? So basically, usually you definitely have a distractor, a copy constructor, a copy assignment operator, and then we add here the move constructor and the move assignment operator, right? So let's talk about some simple stuff. We're going to go back to the move assignment operator. We'll see it again. Any question? No?
So
Yeah.
casting an L value reference to an R value reference, does that take big O of one operation?
So here, right? Basically, when you do move, essentially the only thing that is happening is that you're casting X into the move casts X to an R value reference, right? However, now the vector string temp, essentially the move constructor, now the right side of after temp equals a cast value, R value reference. The right side of this assignment, or the right side is an R value reference. But the same thing is equivalent with the move. The move, that's the only thing that it does. That tells you, and let me just explain how it's done with this example. Okay, let's just go to this example and we'll go back to it. Okay, but you don't have to write this casting. This casting is extremely fast, but you do it with the move, right? So that's a syntactic thing to tell the compiler that the right side is an R value reference, but that has an effect, and we'll see what it means. Okay, so I'm gonna skip this because this talks about the copy constructor and move constructor, but you can look, you can see which functions is which. So let's say we have this simple incel class, but now we make it a little bit more complicated by adding a pointer value. So int star stored value. So stored value now is just the only thing that this class is holding is an integer, a pointer to an integer. Okay, and you have these nice functions here. You have a constructor that is actually allocating memory new int initial value. You read, you just return star stored value, and you write, you just add something to it. You just change the value there. Now, if we go to this test function code, you have an incel A that has a value 2, then you have B equals A, that's another copy constructor, then you have C equals B, then you say A dot write 4. At the end of the day, what would the last C out give me? C out A dot read, B dot read, C dot read. I cannot hear it. Sorry, can you speak louder? So A was initially at 2. I mean, it was a pointer, but the value there, we assigned the value 2 there in this memory location. Then B, instead of B assigned to A, B should be 2, right? Then C is B, C assigned to B, then C should contain 2, but then you say A dot write 4, so A becomes 4. What happens to B and C? Will they stay 2 or they become 4?
2.
It would become 4.
It will become 4, right? It will become 4 because basically here you don't have any the copy constructor, the copy assignment operators are not defined. So basically you have this shallow copy. So basically the default copy that the compiler is going to give you is that for B and C, stored values for B and C will be a pointer to the same thing. They all point to the same thing, right? Does make any sense? Okay, let me try to maybe write that. So A stored value is a pointer, and basically it points to this location. Initially it's 2, right? Then when you say B equals A, essentially B stored value points to, essentially is the same as A stored value. But these are pointers, right? Do you see that? So basically B and A would point to the same location, the stored value of B and A. And when you say C equals B, C stored value essentially will be B dot stored value. But these are basically pointers. So basically they will point to the same thing. So when you say, when you change A stored value, then you change everybody else's, okay? All right. Question. All right.
I have a
So,
question.
yeah, go ahead.
In the last slide, so if you're making a 4 at the end, can't you just put it in the beginning instead of putting the value as 2, like the pointer?
Again?
Like, you know how you put the pointer for A as 2, and then it all switched to 4 at the end. You can, like, would there be an easier way to just make it 4 from the beginning in the main function?
No, this is just the test. It doesn't have any value. This fine. We just try to show some things. It doesn't.
Oh, okay.
Yeah. So that's not how this code is working.
Okay.
Yes. You don't want this, this effect. So basically, the correct implementation though is the problem here is that you don't want them to share this location. So basically, you need to actually implement specifically the distractor that's not implemented there. So whenever you have an allocated memory like new, you need to have a distractor here. You have to delete this value. You need to have a copy constructor. So the copy constructor, as we see here, is the second function here. So the parameter is a constant. Somebody, can you mute somebody? Yeah. So as you see, the parameter that's being passed is an L value reference and incel RHS, right? And then what you're doing here, the stored value now, you create a new memory location, and basically the stored value is independent from the stored value of the previous of RHS, right? The same thing with the copy assignment operator. You pass an RHS on the right side, which is an L value reference, and then you check whether this is the same as address of RHS. So essentially, this means that if this is not the same as the value of the address of RHS, it means that don't do the copy assignment because this and RHS are the same. So essentially, you're saying something of the form A is assigned to A or B is assigned to B. You don't want to do that, okay? And then you return start this, return this thing that you have created so that you can you can use operations of the form A is assigned to B, assigned to C, assigned to D. Questions?
Hey, Professor. So, should I have two questions, but one is that like in the second copy.
Let me do something first before you do that. Let me do something first. I'll mute everybody and then you unmute yourself. Okay. Now, unmute yourself.
So, Professor, in the copy constructor, shouldn't that be a parentheses pointer RHS parentheses dot stored value, or like stored or RHS arrow sign stored value? Because wouldn't the method go first? Yeah, that one. Isn't the method going to go first before the pointer?
No. So basically, essentially, this is like you're doing the curly brackets that we're using there.
No. Shouldn't it be parentheses pointer RHS then close parentheses dot stored value? Because you want to dereference RHS
right.
first.
Maybe yes. Or actually, the easiest thing to say is RHS arrow stored value. It's much easier.
And could you explain this part again? This. Well, what is this?
This refers to the address of the specific object. So basically, if you say, if you go back here, sorry. If you say here C is assigned to B, right? So C is calling the assignment operator. The left-hand side is B. So this is the address of C.
Oh, this is
Okay.
address of C. Okay.
This
And
is the address of C. And RHS at RHS is the address of B, because it's here. B is the right-hand side here, right? C, the left-hand side. I'm sorry. So you don't want them to be the same, because that means that the user is saying B is assigned to B, for instance, and you don't do anything in this case. So if they are different, then you do this assignment operation, which is very simple. You don't have to allocate any memory, and then you return the object that you created. So basically, you return C, basically the object C. So here C, this expression C is assigned to B. It actually has a return value, which is C. And you would ask me why you do that, because you may write things like C is assigned to B, is assigned to A. So the assignments go from right to left, and they return their value. So in order to basically proceed, okay. Let me do something here before we go.
Professor, I have a quick question.
Go ahead, but I just want to just a second. So basically, this is the same as C dot operator equal B. Okay, that's a function. C calls the function operator assignment B. So if you write that, that would work too. Okay, and that function would return the new C. Right? C has changed because of the assignment operation. So if you write something C is B is A, right? Essentially, first the B assigned to A is being called, and then returns B, and then this is going to be assigned to C. So you can check it yourself. If you forget to return this, then you will have a problem. All right. All right. Question?
Yes, for this slide. No. If we go to the next slide. Yeah, this one. So do we do it in this order specifically, or like it can be in any order? Like, does the destructor have
What do
to
you mean
be
by
first?
order? What do you mean what do you mean by order?
By like the destructor and then the copy constructor and then the copy.
No, the order doesn't really matter in some sense. No.
Okay.
Yeah, usually the destructor is you put at the end. Yes, but you know.
Yeah, that's what I was
That doesn't matter. Yeah. Sorry.
Okay, thank you.
Yeah, but now let's move to this the last part, which is like the fun part, because it's new. Is the move constructor. So you can actually write a move constructor, right? Do you see this? And basically, this is like saying, so when will this be used, right? So if you write A equals move C, okay? Or STD. Let's say we're using STD. So A is a constructor. So let's say int cell A move C. So now what really happens is that C was defined before somewhere. So let's say we had int cell C here. Let's say with some value. So C was a nice L value, but now we make it an R value reference with move C. And because you made it an R value reference, if your class has a move constructor, then the move constructor is going to be called. Okay? Does make sense? So now, what is the move constructor? How's it going to look? And usually they're very simple, all right? So this is what the move constructor is doing, okay? So in this particular piece of code, this RHS is actually C that you see down there, right? Okay, is the right-hand side, move C.
Sorry, Professor, I'm a little confused. I see.
Yes.
The move constructor in cell takes in a right-hand side like parameter, right? But you're passing in an L value. So
Say it again.
The move constructor, the parameter takes in a R value, right? It says in cell and
Yes, so
RHS.
yes,
But when
yes,
you're
but
calling move, you're passing in an L value. Is that
right, but the only thing, essentially, the thing you have to realize that the only thing that move does is that it changes the type of C to an R value. So if you go here, sorry, if you go here, text, and you say equals C, or I cannot edit it anyway. If you just say, for instance, that means that C is an L value. It will not go to this move constructor. It will go to the one that we defined before, all right? But this move constructor expects an R value, right? So basically, when you use move of C, then you will go to the move constructor, and that tells you the compiler to call this constructor. And then you, as a programmer, can do whatever you want with this constructor, right? But the way you do it, of course, is another constructor. The way you do it is that you basically, in this case, you don't care about RHS. You can do whatever you want to RHS. C basically is treated as a temporary object, okay? So the way that it's happening, what is happening here? What will it do? Stored value becomes RHS.store value, which means that the stored value of C will be the stored value of A. There's no really copying anything. You're just using the same memory location, right? And the store value of C becomes null pointer, right? So essentially, let me maybe type it here. What really will happen is that after move C, A dot stored value will become C dot stored value. These are pointers, okay? Which means that essentially, in some sense, A stores use the exact same memory location as C, but then the second line that says RHS.store value equals null pointer, the second value means that, which RHS is C in this case, C stored value is null pointer. Which means that we didn't deallocate any memory from C, but basically C cannot access its whatever memory it had before because we stole it in some sense. A just got it, it's a move, okay? So A just moved the items, whatever items they were, into its own memory location. And if stored value was an array of items, a sequence of items, all these items will just be pointed now by stored value, and then then this is what will happen. So essentially, this is what you expect from a move constructor to do. You expect it to basically, I'll use the term steal the memory of the right-hand side really fast and make the right-hand side that usable. Okay? Does it make any sense?
Yes, thank you.
Any questions? Charles?
Yeah, Professor.
Yes.
Yeah. Hey, I just wanted to really quickly ask, like, if you were using the move from the STD library, do you still have to set the other pointer to no pointer?
Okay, so essentially, if you use the move from the SD library, the only thing that it does, this move, is change the right hand side. If you now this incel class is a class that we write. Okay, you write this class. Okay, the STD library, the move does nothing other than change the type of the right hand side when you pass it. Okay. Now, the vectors and the lists and all these things, they have their own implementation of the move constructor. We can see it actually, how it will be possible. And then when you say you have a vector equals move another vector, essentially the vector class already handles it. You don't really have to define it for your vector class, for instance, for a class that's in the STL. But let's say you're doing your own class here, and then you add your own move constructor. This is how it's going to be done for this particular simple class. Okay, any other question?
Yeah, me, Professor. Sorry. Can you please explain again what the dot operator does at RHS.stored value? Are they like synonyms now, or I'm a little confused on that.
Stored value, no. RHS store value is just the RHS is just like an int cell. It has a stored value as a private data member. So RHS
So do they have the same
value is
address now?
No. Yes, store
Okay.
value is the same, is a copy of RHS.store value. So basically, which means that yes, they have the same, they point to the same address. But then RHS.store value becomes null, which means that the right-hand side doesn't see it anymore. So only, in some sense, as I said, the thing has been stolen in some sense, the memory. I use this term. The move assignment operations are also very simple. The only thing is that you are swapping the stored values. Usually, that's what you can do. We swap item by item, and that's the only thing you do. It's very simple, okay? But we're running out of time, so I want to we have a few things to say about this, so we can go back next time and you know ask you have any other questions, answer other questions you may have. As I said, the first assignment is up, and basically you will submit by grade scope. And it basically is going to be something that has to do with the big five, what we described right now, okay? So you'll create a class that is a sequence of pairs of points, of 2D points, right? So we can read it basically. You are given already a header file and a CC file and a make file. So basically you can actually start with something, which is here. It's on Blackboard. Okay, so that's a header file that contains basically a simple class, and it has, you know, the signatures of the constructors, of the distractors, of the move constructors, of the move assignment operators, etc. It has a simple function that says reads points from standard input, and then basically the only thing you have to do, you have to fill out these functions, right? Actually, the way it is right now, it compiles, but it wouldn't do the thing that you want, okay? So you can actually compile it. So this is what I gave you. It will compile, but it will have a lot of warnings, things like that. It wouldn't work the way you want it. Here is the solution. I'm going to show it, but you know, that's the way it's going to work. So basically, you will have a program called test points 2D, and I give you a specific input file to test it with, okay? And then this is what you would expect as the output, okay? So you can read the assignment and you can go over it next time, but basically the source file, the CC, you shouldn't change, okay? You can comment things if you want to see how they work, but you know, this is essentially when we will test it on Gradescope, this file is going to be there with us, the testparse.cc. You don't even have to submit it, okay? But you use it in order to see how these things work. So the only thing we're going to submit on Gradescope will be, as I said at the end, the points2d.h file and the README file, all right? And I gave you an example. That's before we go, and then I will go to the questions here, for instance, right? So I have a test account, and then let's say I want to submit, okay? I will submit the solution that I have, but it has some problems, so we'll see what the problem is. So the only thing I'm going to submit is point2.h and readme file, okay? I'm submitting these guys, okay? I upload it. It says that submitted successfully. Then it's running the auto grade there, all right? And then it will tell me what went wrong or what went right. So basically it's going to compile it and all those things. But as I said, you have to first do it at your own machine or at the lab machine before you send it there. Okay, I'm going through the questions in sequence. So we'll start with Keith and we'll go further down. Just Keith, before you ask the question, so basically the autograde finished. There was a warning in the program So in the compilation, that's not an error. Everything has worked fine. So because of the warning, some the grade was not exactly what you want to be. So basically, not you shouldn't have warnings in your code, but you can see it when you submit. So you can submit earlier to make sure you don't have these warnings, and you can see which warning we have. Okay, go ahead, Keith.
Oh, I forgot to lower my hand from last question.
Okay, Ian. Ian?
Yeah, that's right. So I heard about, I heard someone say about ENIAC before. Will we be using it for this homework?
Yes,
Like,
so basically ENIAC, yes, so basically ENIAC, if you see the syllabus and the description, I mean the programming rules, is the gateway machine. So you log into ENIAC, and then from there you can log into CS Lab machines, and you can test your code there.
Okay,
What
but
saying,
is it required to test our
but you
code
will not
there?
submit. Say again?
Oh, like if we have like Ubuntu or Linux at home, do we really need to use ENIAC to test the code?
No, you don't really need to. You can use your Linux box. Just make sure that the compiler is, if you see the programming rules, you just make sure that the compiler recursion is the same or very similar to the compiler we use for this class.
Oh, okay.
Because
So
for
like,
instance, we have a warning here, so maybe different compilers we don't give you this warning.
oh, okay.
Just to make sure you don't get it. Of course, you will see this warning when you upload. So just make sure that do the assignment on time, do it in your own Linux box, then upload and see if there's any problem with compilation or not. But
Okay.
you can definitely use your own machine. Yeah.
Okay, thank you.
You're welcome. Another question, Amiran?
Yes, Professor. I have a question regarding the outputs that I see here. Is this what you mean by you're not going to get the exact same answer, but that's not a warning? That's just a mismatch in the answer? Because I looked at the homework and the expected output is, for example, do you see after copy constructor 1, C, curly brackets A, it's 74351971. Everything else after that is not part of the expected output. So what do we do in that scenario?
So oh no, this is so basically this is okay. So the auto grader graded in with more data.
Is it possible for us to know this data so we can test it on our computers, or?
Yeah, I can give it to you. Yeah. All right. Yeah, I can change that. But for the moment you can start and then good
Thank
point.
you.
Welcome. But I can always test it in different data. Who else? Amiran, right? Was it Amiran? No. Yes. Yeah. Ahmed.
So on Gradescope, we can submit multiple times before the due date.
Yes.
So
yes,
like
unlimited number of times.
Okay. So as you submit it right here, we can go over it, correct it, and submit it again.
Yeah, and you can just press resubmit and then drag and drop and then.
Oh, okay.
Yes. But don't use Gradescope as a kind of a compile machine that you try to compile and have an error, a compilation error and things like that, right? That would be very bad. You use the resources for just compiling through Gradescope. You have to compile in your own machine and then make sure that it works the way you want it to work, and then upload it and then see whether it works on Gradescope. And you can see whether what would be the result. All right, so don't use this Gradescope for compilation. Say, oh, I submit and I always compile my thing on Gradescope. Okay, don't do that. Just do it after you are done with the assignment. Any other question? Yes, Jan. Is that a question? Okay. All right. So, I guess I'm gonna see you in a few days. As we have office hours, I'm going to announce my Zoom, also my Zoom room for office hours is going to happen on Thursday. And, post questions on Piazza, and then so other students can see it. And, the UTS is doing a great job answering them. And, and we will take it from there. All right. Okay. Any question, Abdul? You want to ask a question before we go?
Is there any
Hello?
office hours? Sorry.
No, go ahead.
Is there any office hours for the TA?
Yes, it's announced on Piazza.
Okay, thank you.
Are you able to go to Piazza?
Yeah, I am.
Yes, yes. So it's there. Everything's announced there. Or on Black. I think it's Piazza, right? Yes. Check Piazza and Blackwood. I'm pretty sure it's on Piazza. Abdul.
Sorry, yeah. What was the program you recommended for us to use again?
The program?
Yeah.
I didn't recommend any program.
You didn't?
No.
Oh, my bad.
I mean, you meant the ENIAC? No, you go to lab machines to test it.
All right. Thank you.
Yeah. All right. Okay. All right, guys. Thanks a lot. So see you soon. Have a good rest of the week. Bye.